Hi, everyone. This is going to be a mini lecture discussing techniques for approaching asymptotic tree recursive problems. Okay, so in this mini lecture, I'll be going over some practice problems, and then I'll be generalizing some ways that you guys can approach these types of problems in the future. Okay, so suppose that we have some sort of function that looks kind of complicated, right? Let's take a look at this function f that I've defined on the right, and we can see that this is the template for how a function with multiple recursive calls will generally look. What I mean by that is it'll have some sort of base case, okay? It'll have some sort of work that this function does, okay? So when we think about a function, it does some sort of work inside of that function, right? This work, in this case, I've replaced with a function call to some function g, okay? In this case, this function g runs in constant time. But the work that a function does may not necessarily be constant time, right? Instead of having this function g here, a possibility is what if I have a for loop that goes n times, right? So we can kind of break up a function into this base case, into the work that function does. In this case, it's calling a function g, but in general, it's just all of the work that's in that function body. And the last piece is going to be the recursive calls, okay? The recursive calls. So breaking up this function into these components helps us approach asymptotic problems, okay? So the first step in this guide that I've created for approaching these types of asymptotic problems is let's draw out a recursive tree, okay? So in this case, what we're trying to do is figure out what is the runtime of the function f, right? And we see here that we have f, all it does is that it calls this function g. In this case, g runs in constant time, and then we have two recursive calls, okay? So let's try to figure out how we can approach this. So what we're going to do first is we're going to draw out the recursive tree. And what that means is we're going to create a node for every function call. So here's how I like to approach that. Suppose that we have some node, okay? For each one of these nodes, I like to have two parts of it, okay? The first part is going to be the input size. The second part is going to be the work done in the function for that input. Okay? In this context, when we look at the first time we call the f function, we're going to be performing constant work, right? Because this g method runs in constant time. So what we're going to say is that we do constant work, and the size of the input the first time we call this f function is going to be n. Okay? Now what I'm going to do is I'm going to incorporate the recursive calls, and we're going to see it's going to grow out into a recursive tree. So let's quickly see what I mean by that. So let's make two recursive calls here. Okay. So my first recursive call, actually both recursive calls, will have an input size of n over 2, right? Which we can kind of see from this example. We see that we're calling it with input size n over 2. Okay. So what I'm going to do is I'm going to add in the input size for these two nodes I've just made. We'll say they're both input size n over 2. And then I like to just have like these little connectors, but it's just more of like pictorially. Okay. So what we'll notice is that every time we call this f function, the size of the input just decreases or gets divided by 2 each time. Okay. And what we'll also notice is that the work done for each function call is always constant because g runs in constant time, and the only work that the f function is doing is calling the function g. So what we will see is we will have this type of recursive tree. I'm going to create one more layer. Give me a second. Let me just do my art skills. Okay. So this is the recursive tree that we kind of see develop, okay? And I only recommend drawing around 3 levels of this tree. 3 levels is enough usually, because it kind of gives us the pattern of what's happening, okay? So just to recap what we've done so far is we've taken this f function and we've said, in order to figure out its runtime, it's best if we represent the series of recursive calls as a recursive tree, okay? For each node in this recursive tree, we've split it up into 2 parts. The first part is going to be the input size. The second part is going to be the work done by the function f for that input size, right? Okay, so now with this tree in mind, let's move on to the second step, okay? The second step in this process is let's try to figure out the work done per level in this tree that we've made. Because once we've made this tree, this is actually the most important part of the process, I think, okay? So we have this recursive tree. So we need to make some sense out of it, okay? What we're going to do is we're going to try to figure out the work done at each level of this tree, okay? So when I say a level of the tree, we can kind of think about this is one level of the tree, okay? So on this left-hand side, I'm going to create this column called work per level, okay? This is just work per level. So at the first level of this tree, what we'll notice is that the only work that we're actually doing is one work, right? So in this work per level, I'm going to say I do one work at this level of the tree. Looking at the second level of this tree, what we'll notice is we're doing 2 work. So what I'll put here is 2. Then if we look at this next level, we'll see that we're doing 4 work, okay? So we'll put a 4 here. And then so on, right? So the next step is once we figure out how much work we're doing per level, we need to recognize which sum that we're dealing with, okay? Because our end goal here is very important to understand what our end goal is that we need to figure out the total amount of work that we're doing, okay? So our end goal is to find total work, right? The total work a function does is the runtime of that function, okay? So to find the total work, what we can do is figure out the sum of each work per level, right? So in this case, what we can see is that the total work we're going to be doing is going to be the work on the first level, plus the work on the second level, plus the work on the third level, and so on, until we get to the bottom level. So what we can see is that the total work we're doing for this recursive tree will take the sum of 1 plus 2 plus 4 plus 8 plus so on, okay? So we should recognize which sum we're dealing with, because when we look at the sum that's in this column right here, what we'll notice, which is really cool, is that for this class, nearly always it'll be one of these 3 sums over here, okay? So in this case, what we can notice is that our sum is going to be a sum I like to call a dominating sum, this sum right here. So what I mean by that is in a dominating sum, the last term in the sum dominates all of the other terms, okay? So I'll explain that once more. When we think about a dominating sum, it's characterized by this principle that the last term in the sum dominates all the other terms. So what I mean by this is that if we have a dominating sum and we're trying to figure out what is this sum equal to, all we need to know is what's the last term in this sum. Because if this last term in the sum is so big that we can ignore all of the terms before it, the sum asymptotically comes down to what's that last term, okay? In this case, the following sum is an example of a dominating sum, okay? Some other examples of dominating sums are like 1 plus 3 plus 9 plus 27, okay? And so on. So now that we have this dominating sum and we've recognized that when we look at the work per level and we're trying to figure out the total work of this function, all we have to do is figure out the value of this sum. So to figure out the value of the sum, what we know is that we need to figure out what this last term of the sum is. So what is the last term of this sum? So to recap, we need the last term of the sum above. And if we find the last term, that's going to be the runtime of our function. I think that's really cool. So how are we trying to figure out the last term of this sum? And it's going to be like a bit trickier than we're going to anticipate. But the first step into finding the last term of this sum is we need to figure out the height of the tree. Okay? So what is the height of the tree? Because to figure out the last term in the sum, we need to figure out how many nodes are at the bottom layer of the tree, right? Because that's in essence what we're doing here. So to figure out the height of the tree, there's a couple ways that we can approach it. What we can do in this case is we can recognize that the height of the tree is going to be log base n. So how in the world did I get to the height of the tree being log base n? Well, I've done a lot of these problems, so I recognize that this is a tree whose height is log n. So I'm going to quickly prove to you guys why this is the case, so you guys realize this in the future. So in general, if we ever have a tree that looks exactly like this one right here, for the sake of this class, you guys can just take it for granted that the height of this tree is log n. So why is this the case, you guys might ask? Okay, so when we think about a logarithmic relationship, so some function having a log base n runtime implies that doubling the input increases the work, or height in our case, by 1. Okay, this is the characterization of a logarithmic relationship. Okay, so suppose that we have the following tree, and I say, let's double the total amount of elements in the tree. Okay, so let's consider that suppose that this tree had a total of n elements. Actually, I'm going to use a different number to not confuse us with the original n. Let's say this tree had k elements. Okay, so now I'm going to say, what if we decide to add another k elements in this tree, so our tree has a total of 2k elements? My question to you guys is, how does the height of this tree change? Well, if we double the elements, we're only really going to increase the height of the tree by 1, right? Because what's going to happen is if we have this tree right here, like suppose we have some tree, and we decide, hey, let's double the total number of elements, all that we're going to do is we'll take this tree, we'll double it, right? And then we'll create a new node right there. So you guys can kind of see that doubling the total number of elements in this tree increases the height by 1, which implies a logarithmic relationship. Okay? Okay, so now that we've figured out what the height of the tree is, in this case, it's going to be log base n, the next question I have is, how does this help us figure out the last term in this sum, right? because that's what we really wanted to figure out, was the last term in this sum, so we could actually figure out the runtime of this function. Okay, so let's try to figure out how we can utilize the height of this tree to figure out this last term in the sum. So going back here, we need the last term of the sum, and we know the height of the tree is log base n. So what I'm going to argue now is that we can rewrite the work per level, in this case, to be 2 to the level, okay, where L is equal to the level we are on. So why can we do this? Well, let's look at this image we have here. I'm just going to move it down. Okay, so if we're thinking about the work per level, my claim is that another way of thinking about the work per level is to say that this is equal to 2 to the L, where L is the current level. Okay, so how are we classifying the levels of this tree? Let's say that this is level 0, this is level 1, and this is level 2. And what we'll notice is that the work per level is simply going to be 2 to the level, right? In this case, we see that this is 2 to the 0, and this is 2 to the 1, right? And this is 2 squared. Okay, so what we've successfully done is we figured out, here's another way to identify the work per level. Now what we can do, which is really cool, is that the sum before that we had was 1 plus 2 plus 4 plus 8. I just assumed 8 was the next one, plus so on, right? Where this is like the last term that we want. Now what I'm going to say is that we can say this is 2 to the 0, plus 2 to the first, plus 2 to the second, plus, this is the important term, 2 to the h, okay? Because we know that the bottom level of this tree has the property where L is equal to h, where h is the height of the tree. So now what I'm saying is I can rewrite the sum from before, this sum, in terms of this, which allows us to identify the last term of this sum much easier, right? Now we've noticed that the last term in this sum is 2 to the h, okay? So if the last term of this sum is 2 to the h, and we know that h is equal to the height of the tree, which is equal to log base 2 of n, what we can say is that this sum becomes 2 to the log base n, and we know, using our logarithmic math, that this is the same as n. So what we've essentially done is we figured out that the total work that this function is doing is going to be 1 plus 2 plus 4 plus 8 plus n, right? And what we can say is that this sum is a dominating sum where this last term dominates. So we can output our final answer to be theta of n is going to be the runtime of this function. Okay, so hopefully this made sense. If this didn't make sense, I'm going to walk through a couple more examples so we can really try to understand how we can apply this same 4 steps to any future problem. Okay, so let's walk through a couple more problems. And they're not actually going to be different problems. I kind of lied. All I'm going to do is I'm going to say, what if g took a different amount of time? Okay, so now let's say, what if the g function always takes linear time? Okay, in this case, let's explore how the total runtime changes. So what I'm going to do is I'm going to use this bright blue color to say, let's go through all of the steps before and just note what changes and how it changes. So we could try to figure out the runtime in this case, okay? So what we're going to change here is that we will still have the same shape of the tree, we're just going to have a different amount of work done at each node, right? What I mean by that is this first node is doing n work, right? Because the g function now takes theta of n time. So that means the first time we call the f function, the g of n takes n time. And applying the same logic, we can say that we will always execute work proportional to the input size. So we can kind of fill in all of these nodes as follows. Okay, so with this updated tree, the next thing that we can do is let's try to figure out the work per level, right? That's the next step. Let's keep going. We get rid of that. Okay. So we're trying to figure out the work per level. So let's create another column here. So the top layer of this tree, the top level, is doing n work, right? The second level of this tree is going to be doing n over 2 plus n over 2 work. So it's also going to be doing n work, right? If we look at the next level of this tree, what we'll notice, which is really, really cool, is that each level of this tree is actually doing n work. So what we can say is that to find the total sum, we just need to figure out the total number of levels and then multiply that by n, right? So the sum that we're dealing with in this case is going to be this constant sum, okay? So the next thing that we need to figure out is how many terms are in this constant sum, right? In this case, it's actually not too hard because we knew the height of this tree is still log base n. So what we can say is that, let me get rid of some of this stuff from last time. Okay, what we can say is that if the height of the tree is log n, and we're doing n work per level, the total work in this case is going to be equal to the work done per level times the number of levels, right? Which this thing is the same as the height. So we see the total work is going to be equal to n times log n. And we get the final answer in this case is going to be n log n. Okay? So this is like another example. And I'm going to walk through one final example. I'll make this one on the faster side, just to show you guys a pattern at the end of what develops here. Okay? So now let's say that this function is n squared. Okay? So now g of n takes n squared time. So let's try to figure out how the runtime changes. Okay? So now what we'll notice is that the work done at each function call is going to be quadratic of the input size, right? So now we're going to be doing n squared work here. At this node, we'll be doing n over 2 squared work, and so on for all of these nodes. Okay? And what we'll notice is that I'm going to quickly fill out a couple of these just so we can calculate the work per level, is that this will be n squared. This will be n squared over 4. This will also be n squared over 4. This will be n squared over 16, right? I'm just doing the math. And now what we'll notice is that the work done per level is the following sum, right? And because when we combine these two terms together, we see n squared over 4 plus n squared over 4 is n squared over 2, and then so on for the next level. So now what we'll notice is that this sum may look a bit different than the other ones we've seen so far, right? The sum that we have right now, just to recap, is the sum. Okay, let me rewrite the sum right here. Of n squared plus n squared over 2 plus n squared over 4 plus so on. And now what we're going to notice, which is really cool, is that in this sum, it's a dominating sum where this term dominates. And how I'm going to prove that to you guys is if we think about this sum, it's basically the same exact as the dominating sum in the example. It's just written in reverse order. Okay? My claim, it's the same exact as this dominating sum, is just written in reverse order. Because all this dominating sum is doing is that we multiply by 2 each time. In this sum, we're just dividing by 2 each time. So it's in essence the same dominating sum in reverse order, which tells us that the runtime of this dominating sum is the first term in the sum, because it's in reverse order this time. So what we can say is that the total runtime of our function is going to be the first term in the sum, which is n squared. So our total runtime is going to be n squared. Okay? And the last thing I want to conclude on are some takeaways here. Okay? So looking at this recursive tree, there's some cool things we can take away. And this is not completely needed for solving these problems in the future, but I think it's fun to understand and fun to notice. So if we ever have some sort of recursive tree like so, what we'll notice is that there were three examples we walked through. Okay? I'm going to put those examples side by side here. Okay? So this is the work per level for each of the examples, the first one, the second one, and the third one. Okay? So what we'll notice is that in the first example, we kind of had the following sum. And what we notice in this example is that the total amount of work that we were doing was kind of congregated at the bottom of the tree. Okay? So in example 1, the total work was congregated at the bottom of the tree, right? Because we had the sum 1 plus 2 plus 4 all the way up till n. So we knew that bottom level was the only level that really mattered. Okay, now I'm going to jump to the last example where we had this following sum. And the opposite thing kind of happens here is where the total amount of work is kind of congregated at the top of the tree. Okay, so in this example, what you guys will notice is that the total work is congregated at the top node. Okay, and then the middle example, if you guys recall, went n, n, n. So if we kind of think about this middle example, we can say that the total work is spread evenly. So what's really cool here is that if we ever have the recursive pattern of dividing the input size, in this case, we always executed the call f of n over 2. If we ever have some sort of function call where it's like the input divided by some constant here, then we will always have one of these three things happen, where the work is either all at the top, all at the bottom, or spread evenly throughout. If and only if we see we're dividing the input by some constant every time. So that's just one really cool takeaway. But this isn't the case if we have some sort of function like f of n minus 1. In this case, what we will probably see, which we didn't really get to cover in this video, is the sum of this arithmetic sum right here. And this usually happens if we have the input size changing by a constant every time, right? Something along the lines of f of n minus 1. So that is all for this video walkthrough. I hope you guys found this helpful, and I definitely recommend using this same strategy as you guys approach tree recursive asymptotic problems in the future. Yes, that is all.